All right, welcome. Everybody here?
Yep.
Yep. We're off and running.
Those of us who are here are here.
So this is kind of a presentation meant to be interactive. I hope that anybody that has a question, ask me as we continue on. Don't wait until the end. Any of the materials that I'm going to present, I'd be happy to give to anybody and help them with these kind of projects.
Mm-hmm.
This is what we're going to talk about. This is a GPS-based clock. It uses Arduinos to capture the GPS information and display it.
That's pretty.
The project that I wanted is I wanted to make a clock that displayed UTC for obvious amateur radio use, also the local date, and then the location. And with the location, then you can have the Arduino calculate the grid square. And I wanted to put it on at least a 4-line display, because if I put it on a 2-line or a 1-line, you'd be scrolling information all the time. This way you can see all the information at one time. And this project kind of encompasses my hobby interest. My background is electronics. I love computers. Amateur radio came into my life, and on top of it, 3D printing. So this project puts all of those together in one thing. I wanted the clock to do information that would be useful for an amateur radio operator, and hopefully that's what it does. It's a very precise clock. It's good to 30 nanoseconds of accuracy, if you could actually figure that out.
Then it might be cool enough for FT8.
Say that again?
I was just being a bad guy.
Okay.
Making a joke that wasn't funny.
So the design criteria was use inexpensive everything. I wanted to make this as relatively cheaply as possible, although I did pick an Arduino that's a little more spendy than some of them. But one could go back and make it even cheaper than I did by quite a bit. These things are the GPS modules. They come in all kinds of sizes. You can buy them on Amazon almost any time for probably $15 to $20. If you go out and shop around on eBay, these things go from $4 on up. So they're pretty inexpensive. They tend to put out a pulse per second. They put out a serial stream, and some of them you can plug a USB into them and tie them directly to a computer. Some of them have external antennas, some of them have internal antennas, some of them have both, but they come in a variety of flavors. You can get some really, really nice ones that will tell you course and speed and how fast your ship is going and all that wonderful stuff, but these are cheap. The Arduino, you can see the pinout in the thing, is an Arduino Nano Every. The Every board is a 16-bit processor instead of the usual 8. Has lots of extra memory, but it's the same form factor. It's probably about 1.5 inches long, 3/4 of an inch wide, small little guy. You can tie a variety of peripherals to this. You can plug in a USB cord. You can plug in serial cords. On board, these things are 5-volt regulators, 3.3-volt regulators for newer things. They also have analog inputs, so you can do things like direct temperature measurement or almost anything. In this case, I use the analog input to get a voltage from a potentiometer, and I use that voltage to determine what the time zone you're in. So powerful little chips. This thing is about $10. The GPS system has been out, as everybody knows, for quite a while. The little GPS modules tend to receive sentences, they're called, and these sentences are very random. So one minute you might get a sentence that is time and date, the next sentence might be location, the next might be speed, and so you have no idea when you're going to get the sentence you actually want. So you have to always be able to read your little GPS, and so that changes how you're coding it. But there's a lot of information available coming down from the GPS satellites, and you can pretty well pick and choose what you'd like to utilize. This is kind of the overview of this project. They're called fritzing diagrams. In the upper right corner is the GPS module. The thing to the black thing to the left is a display, whatever one you might want to use. The Arduino down in the lower right, and a little potentiometer. And this is all the wiring that's needed. So it's not a whole lot of wiring necessary for this project. So it's pretty easy to solder up.
Crazy question.
Okay.
Have you got an actual picture of a relative size of the module? Like next to a penny or something, so we can get an idea of its size?
Hang in there, and before this is said over, you'll get to see actual sizes.
Excellent.
How's that? I don't know if anybody can actually see this, but this is just a quick parts list. And most of these, if you went out to eBay, you can get them for a fraction of what I did. I just tend to order from Amazon because it shows up in a couple of days, so that's always nice. Here's my logic diagram, and you probably can't read that depending on your resolution, but basically you initialize the Arduino, you get it all set up, and then you start polling the GPS module, and you keep polling it. And did it have a date sentence? Yes, it's got a date sentence. Extract all the information for date, then move on and go check the next sentence, and then loop yourself back to the GPS, because you can't go do something else. You've got to make sure you're always reading the GPS, because if you don't get back to it, you will miss part of the sentence and just get gibberish. So it's really critical in these things that you read the GPS module as often as you can. And so it reads the time and date, gathers the information, converts it into the UTC format, converts it into local format, and then sends it to the display, comes back and then sees if there's any location information, comes back, says, is there any elevation information? I also have it tell me how many satellites it's acquired, because the more satellites, the more precise the information is, etc. Software to do this. The joy of this project is the software is free. Out in the world, there is the Arduino Integrated Development Environment, and it's available from Arduino CC in Italy. It will run on both Mac and Windows. And the Arduino is programmed in C++, which is a bit of a complicated language, but the basic mode is pretty easy, and there is just an absolute boatload of code already out there on the internet. So even if you don't know the language well, you can put together Arduino projects without really knowing that much code. The other end of this was, how do you make a case? And Fusion 360, which is an AutoCAD Autodesk product, allows 3D design, and they have a free version for home hobbyists. And so you can do full 3D modeling of almost anything. But in my case, I used to 3D model cases. And Jay, you were asking about relative sizes. The little breadboard is about 3 inches long by 2 inches wide. So you can see the size of the actual Arduino processor in there. You guys all know what a potentiometer is. There's the potentiometer sitting there. And, you know, I use a breadboard to start out. You can transfer the diagram from that Fritzing diagram onto a breadboard. Once you get it there, you can start programming with your code and see if it does what you want it to do. And when you finally get it all working, well, I say, you can just keep trying your code until you do get it working. It took me quite a while to get a clock that didn't have little errors. And I think it actually works pretty good at this moment. In the right lower corner is the Arduino IDE, the Integrated Development Environment, and kind of gives you an idea what it might look like. And this is the Fusion 360 side. Autodesk has the Fusion 360. In the lower right corner is what the image looks like. I started my design with this 3D printed case. Now, I designed this case. It's a plastic case that is 3D printed. This is one that I made the raw case. It's a snap fit. So it's just a snap fit plastic box at this point. You can see the little tabs. This is completely sizable. So if I wanted a 6x6x3 or a 2x2x1 or whatever size, I just go in and tell it what size I want my finished object, and Fusion will scale everything. And this is my starting spot. And so the next phase is, okay, I've measured the display module. And so I would size this case, and I started sizing the case and told Fusion to cut out the hole. The display module has solder joints up on the upper side, so you can see a kind of a slot where the solder pigtails stick out, and that's cut in there so it won't, it'll lay flat. Once I got the 4-line display fitted into the case, then I started, where do I put the microprocessor? So I designed a slotted design so the microprocessor board will literally slide in there and not need any hardware to bolt it to the case. And then the back side of the case, where the USB connector is going, I just made a hole later on to plug into the Arduino. On the left side of the case, I put in a buck converter if anybody wanted to power it off of like 20 volts or 12 volts or anything in between. It would then drop the voltage down to the 5 for the Arduino, and so that was my little slot for the buck converter. This is the back of the case. In the upper right of the case is a slot where the GPS module slides in. The center hole is for a power connector for higher voltages, and on the left lower corner is the USB slot to take a USB. The thing is powered off of USB normally, so it just plugs into any USB connection. And you can see a bit around the lid there. There's the female side of the snap case. So this just literally snaps into the whole case. Once the case is designed, I send the files out to what's called a slicer. So Fusion makes a STL file. The STL file is loaded into a program that slices the file up into layers. And this 3D printer in this picture prints one layer at a time. So it will take the sliced layers and print a layer of plastic, move up a fraction of a millimeter, print the next layer, move up a fraction, print the next, and slowly but surely it will print an entire object. This case takes about 4 hours to print with a 3D printer. Anybody else got into 3D printers?
Well, I know Kai does.
Ah, good. I'm just surprised. As a home electronics hobbyist, this is the neatest thing this is better than sliced bread, because you can just make whatever you'd like out of these things. This is the finished case with the parts mounted in there. The display in the back, the boost or buck converter on the left, and the Arduino on the right. And so I fit all the parts in. That allows me to figure out wire sizes, what do I need to run from the Arduino to the display, from the buck converter to the display, out to the lid, etc. And with that, I go over to my little soldering station here. Now this can all be soldered on your desktop, but I acquired this wonderful binocular microscope, and for old people it makes soldering a wonderful thing to do. I've used lead-free solder, given up on lead. The main reason I gave up on lead is because my cat came into my office one day and decided to eat half the roll of lead solder, and spent a considerable amount of time down at the vet at the end of the street. So I've switched to lead-free solder after that one. The other one, if you're doing soldering nowadays, fluxes. I found that, boy, adding a little bit of flux on top of whatever you're doing makes soldering much, much easier. And the third thing I do is I found silicon-coated wires are out there now, and boy, do they make it easy to do soldering projects.
Question on soldering.
Yeah.
Yeah, I just had a friend of mine, we all know Carl, and he did a little bit of plastic surgery on my rig, and he had some non-lead solder, and it was failing to play nice, and he said it might be too old because it's got some kind of organic flux. And so we switched over to my old tried and true lead solder, and it flowed beautifully. Is there a time limit on lead-free solder and the fluxes that they may contain?
Well, the fluxes are just resins, literally like rosin off a tree. And so, yeah, they'll go bad in time. But the answer is the lead-free stuff just doesn't stick as well. So if you don't add your own flux on top of it, I find that it just doesn't do a great job. But a little bit of additional flux will flow lead-free solders really well. And but
does it require a little additional heat?
Not so much the additional heat, the additional flux.
Okay. Very good.
It'll change how you look at lead-free solders.
Right. I didn't have any lead-free. I just, my kit was dated.
Indeed. Well, this is the finished clock. Plugged into a USB connection, it powers at 5 volts. It uses in this form 1.13 amps, so about 0.6 of a watt. So it's not a big drawer. You can sit in your office and run 24/7. The joy of these clocks in my world is you unplug it, turn it off. When you plug it in, it goes and gets a new GPS signal and is instantly as accurate as anything you could have. So power goes off, this will come back and re-get its signal, and off you go again. So you don't have to worry about the battery dying or whatever. It will just start from scratch every time. Some of these little more spendy GPS modules have a built-in either battery, or they'll have a super cap on them now that will hold the information and start up the GPS even faster.
Cool. Can you explain the displays line by line?
I can. The top line is pretty easy. It's that was.
And we lost your pic. Oh, there it is.
It'll come back. It was 6/13/21, obviously month, day, year. Time is 2:39:34 on Sunday, and that's UTC, Greenwich.
Oh, okay.
The next line is currently under longitude, 120 minus 124.66551, and in a second
Grid.
it will display latitude. So it flashes between longitude and latitude, and I did that because I don't have enough room to put the whole amount there, and if I shorten it, then it's not that accurate. So I have it go from latitude to longitude, and then on the right is your grid square. And so if you took this to New Mexico, it would calculate your latitude, longitude there, and calculate your grid square wherever you are.
That's cool.
Next line is local time, and you'll see that at this one it's Saturday locally and Sunday UTC.
Yeah.
And then the bottom one, the blank spot is because at this time it hasn't come up, but there's a quality signal. They'll tell you if it's 1D, 3D, how accurate it's going. The number of satellites is sitting there, currently 0, but it'll usually it's 9 or 10. And E is elevation, and unfortunately, minus 65 is pretty accurate for elevation on GPS, even though I'm probably 65 feet above sea level.
I'm not sure why is that?
The GPS elevation is like plus or minus 5 meters or more at best.
Well, that would definitely be or more.
It's because the constellation is more XY. They're orbiting and all that stuff. It's always been that way.
Yeah. And I say if you get the $200 GPS module, you probably get better elevation information, but the $8 module probably doesn't cut it.
Wow. So the original photo, looking under the skirt and looking at the display and the modules, that's the entire unit, including the GPS chip. Yes.
This is minus the GPS chip.
Oh, okay.
That's mounted on the lid.
Okay.
And the reason I mounted it, because if I tried adding another mounting bracket on the top, then the display might not slide in, or I'd need to make the case bigger. So I just decided that I would design it to go mount on the lid instead of mounting it on the rest of the case.
Very cool.
And that's basically this whole thing in a nutshell. I don't know if anybody would have an interest in one of these, but I would be more than happy to help them if they needed help programming, if they would like somebody to 3D print anything. But I found it's a great little project, and it's one that's useful when I'm contesting.